man spricht irgendwie anders, wenn man weiß, also ich finde mich sonst selber, dass ich irgendwie das zu leise und zu...
Okay.
Ja.
So as a final lecture for today, we have Johannes who tells us more about Zeta values.
Yes, thanks for the introduction to the second lecture. I understand it's rather late in the afternoon, and also for people listening it's a long day. So I'll try to keep you awake and tell a little more about multiple zeta values still at genus 1. Nevertheless, at the very end of the lecture, I hope to get the transmission or translation to genus 1 from genus 0. Now, let's recall what happened in the last lecture. I introduced the multiple zeta values, zeta of n1 to nr, and I introduced as well another way of writing them in terms of letters which were from 0 and 1, whereas here the elements ni were from the natural numbers. And this second way of writing the zeta values was related to an integral representation where I chose two differential forms. The first differential form, omega 0, was just dt over t, where omega 1 was dt over t minus 1, and then one could rewrite every of these multiple zeta values in terms of an iterated integral over these differential forms here. And the translation between those two was that each index n1 would be, and I'll put it, I'll put it here, n1 would lead to a succession of numbers starting with the 0, with the 1, and then a lot of zeros, which was just of length n1. And I demonstrated that at one of the examples for the shuffle and one example for the Stuffle relations. Now, you might have recognized Julian's question at the end of the last lecture. He said, oh, you are writing down that zeta 1, 2 is equal to zeta 3, and if I apply these shuffle and Stuffle relations, then I have trouble making sense out of that, because you have told me that one of the necessary convergence conditions on these zeta values is that nr, that is the last index here, is larger or equal to 2. And yes, if you just write down the sum 1 over I for a sum 0 from I to infinity, you get, of course, a divergence. And you don't want that. Nevertheless, it is an interesting question, and it's actually a rather deep mathematical question of whether one can define some way of making sense of these zeta values which are forbidden in the way here. And this is known as a concept called regularization of zeta values, and is not at all independent from the regularization of iterated integrals which are polylogarithms. So for polylogarithms, you need to regularize sometimes if your base point, which is the lower integration limit, leads to a divergent integrand. The same is true in the multiple zeta value. So let us get back to the definition of the polylogarithm, and let's do something forbidden and write down what the G0 of x actually is. Applying the definition of the integral, we would write down this is the integral of 0 to x dt over t. So we have the differential form omega 0 here. And that looks pretty much like a logarithm, but it is not really a logarithm. So let's put a question mark here. So it would be nice if this is the logarithm, and I wouldn't write this down if after agreeing on a proper regularization convention, this will be the logarithm. Nevertheless, for now, it's not. And if you write down the definition of the logarithm, then the logarithm is defined as the integral from 1 to x dt over t. And in order to make the equation to be a correct equation, we better add another integral from 0 to 1 dt over t. And of course, there's a lot of divergent things on the blackboard right now, and we'll agree on a convention to make sense of these things immediately. So in particular, if you calculate here from 0 to 1, of course you get a divergence here because the t is in the denominator, and things will not improve substantially if we write down what g1 of x actually is. So how to resolve that issue? Somehow we do have a part here which we wouldn't like to have. We would like, in the sense that these are polylogarithms, somehow find a relation between the logarithm of x and this g0. And yes, there is a solution, and we'll define the following conventions. Define that zeta of 0, and I want to make clear that this 0 is a 0 of the labels 0 and 1, not to be confused with zeta of 0, the Riemann zeta, at the position z equals 0, which is minus 1/2. So that zeta of 0 is nothing else as g of 0 evaluated at 1. And this is, of course, the integral 0 to 1 dt over t. And we define this to be 0. This is a regularization convention which goes nicely along with the same line of thinking for polylogarithms, but for now I would like to stick with the definition here. Let us define zeta of 0, where 0 is the sign for this differential form, to be 0. And at the same time, I would like to define what zeta of 1 is. This is minus g of 1 comma 1. The minus is because here we have a n1, which is 1. And this is nothing else as the integral 0 to 1 dt over t minus 1, if I were allowed to write it this way. And this is going to be 0 as well. There is better ways to write that down. One can introduce some other notation and will not write something which is as fishy as these two lines on the blackboard. So whatever is in the middle here, or whatever is in the integrals here, this is just to remind you what it would be if you write it down. And we will from now on define what it actually means, what a zeta of 0 and a zeta of 1 is. And now, since we made this kind of agreement, we can say that any zeta value which was forbidden before can somehow, or should be, and I'll show how that works, be related using this convention to allowed zeta values. And this whole construction, I said it already, it goes under the name of regularization of zeta values, and I'll show on an example what the idea is. So let me write down relate all forbidden multiple zeta values to allowed or admissible MZVs using shuffle identities. So the first thing to note is that whenever there is a product of, or whenever there is a zeta value which just has ones, and this is again from the alphabet 0 and 1 here, in the label, this is proportional to zeta 1 to the power n, so there's a factor of 1 over n factorial here. Because you can choose shuffle, you have n factorial different ways of ordering the zeta of ones in order to get a zeta with many ones in here, and that better be 0. The next situation, which is difficult and which would lead to a divergent zeta value, is the following. If you have a 1 at the end here, that would mean that NR, the last index, would be just 1, and we would have no zeros which would fill up on the right, and that would lead to a divergent 0. And so we will consider as an example zeta of 1 or 1, which is zeta of 2, 1, and the 2, 1 is the problem here, because this would be a forbidden zeta. Nevertheless, we can consider the following product. So you consider zeta of 1, 0 times zeta of 1. This whole product better be 0, because we agreed that zeta of 1 is 0. But now one can perform the shuffle operation, and shuffle operation will lead to zeta of 1 or 1. And then I will have 2 copies of zeta 1, 1, 0, because I can place the 1 from the single zeta between 1 and 0 and at the first position. So I get twice zeta of 1, 1, and 0. And I can rewrite it in the, let me call that the n language. This is nothing else as zeta of 2, 1 plus 2 zeta of 1, 2. This here is perfectly fine, while this one is a forbidden one. But since we know that the right-hand side is 0, we can simply use that as a definition for the forbidden zeta value. And of course, you immediately find that zeta of 2, 1 is equal to minus 2 zeta of 1, 2. But the point I would like to make here is that although it works beautifully for this example, one can show that recursively any did I make a mistake? Something wrong? If I bring this to the other side, it should be minus 2, I think. No? I think this is right. Yeah. So I was about to say that while it works beautifully on this particular example, there is a recursive way which allows you to de-shuffle all the divergent indices from a zeta value. So whenever you get a 1 at the very last position, you precisely do what I did right now. you rewrite the zeta value as a product which will be 0 in total. You get a linear equation and you can solve for the forbidden zeta value. And of course, if there should be a situation where you get 2 1s or 3 1s at the end, you can do that a couple of times. And that is the notion I will be using during the remainder of these lectures, and which basically everybody is using. It is the shuffle regularization, and it's called shuffle regularization because it's compatible with the shuffle operation. In fact, it even defines the non-allowed zeta values with the shuffle operation, through the shuffle operation. What is wrong, though, is now to go back, use that identity, and then rewrite this as a sum again. Yeah? This one you can easily rewrite as a double sum, but this one you better don't. So, of course, this is wrong. So, because in the sum, if you would use the sum formulation, we should better also translate these two conditions in the sum representation. We don't want to do that. Let's just stick to this kind of formulation here. A second remark I would like to make here is this looks like a rather ad hoc procedure. I already said that one can show that defining these two properties here is something which can be very well explained from the regularization of polylogarithms. Even more, once we will encounter properties of elliptic multiple zeta values, one will be able to see that these two conditions have their analogs at genus 1 as well. So one can actually show that this type of regularization is in some way, in some sense, canonical, and it is the, or say, not the only, but a very useful way of regularizing these multiple zeta values. Okay, any questions so far? It is not obvious, but one can prove that there are no inconsistencies. Part of the proof is that you define the things through the shuffle relations, and you can show that once you want to have it an algebra homomorphism with respect to the shuffle product, then this is the unique solution. Yeah?
Could you also set up some regulator that just stops the integral at some epsilon?
Yes, that is something you can do. So what you do here, you basically set the integral for the logarithm, which is, you basically write down that this area shall play no role. And I could rephrase your question by saying, can I choose a different base point than just the 0? And the answer is yes, you can do the complete shuffle regularization with a different base point. Yeah, so you don't need to choose 0, you can also choose something else. Yeah. Okay, now already when I repeated from last time that we have these two formulations, I mentioned that in this formulation the shuffle relations are more beautifully expressed, while here the shuffle relations are very natural. And a mathematician and probably a physicist as well would immediately ask, isn't there a language which allows to cover all these relations for the multiple zeta values in one language and not have two ways of expressing these things which seem to be not slightly incompatible but are very different in nature? And yes, such a formulation actually does exist, and the bad news is that introducing that language properly mathematically doesn't fit in these lectures. So you might have heard about the word motivic coaction or motivic multiple zeta values, and there's a whole mathematical beautiful formalism which allows to remedy a couple of the shortcomings of this formulation. The first thing is that, and I will write on the blackboard what that is, that there is the so-called F alphabet language, which is another way of expressing multiple zeta values. And the main feature of the F alphabet is that there is only shuffle relations between the multiple zeta values expressed in that language. The second ingredient, or one other ingredient for the motivic formalism is an algebraic one. So one can consider, of course, the zeta values as these iterated integrals and then show that there is a algebraic structure, a Hopf algebraic structure with a product and a coproduct. A Hopf algebra is an algebra which is its own bi-algebra, and there are some compatibility conditions between a product, which will be the usual product, or the shuffle product, and the coproduct. The coproduct will somehow disassemble the multiple zeta values. That is something which I'm very happy to give some references to read upon. It is a beautiful theory, and it has been developed by numerous people during the last, say, 15 years. Now, what I would like to do here, I would like to write down a couple of examples of these zeta values in the F language, and would like to leave the working out of the exact formalism with the coproduct to those which are interested in coding this up. So this is not a one afternoon thing, it's something which takes a little longer. So first of all, let's state the following thing. Every multiple zeta value can be rewritten as linear combination plus as linear combination of words of the form F2I1 plus 1 F2IR plus 1 F2 to the power k, and here the i's are from the natural numbers and k is also from the natural numbers. So that is, every multiple zeta value can be rewritten as a word with f's with odd labels, a lot of them. They are not commuting, so the position matters. That is why it's called letters, and the whole thing is called a word. And at the very end, there is the F2s, and the F2s, they are collected at the very end because every even zeta value could be, that was the beginning of the first lecture, expressed as a power of zeta 2 with these Bernoulli numbers. So in this alphabet, you actually can see that the even zeta values take a special role mathematically. One would say it is algebra co-module because of the special role of this F2 to the power k. And then one can, on a proper, let me call it a proper motivic generalization of multiple zeta values, define a map which Francis Brown, who worked out that map, is calling the phi map in a way such that the phi map is again an algebra homomorphism. So if you have two words x1 and x2, then this phi of x1 shuffled with phi of x2 will be an algebra homomorphism that is a concatenation of the words, and then applying the phi map is the same as taking the result of the phi map and shuffling the words f. Yeah, it's a homomorphism. And then there is a couple of identities I would like to write down, and the whole mathematics is unfortunately hidden in the little letter m, which is for motivic, and this is what I mean by a proper generalization of multiple zeta values. Francis Brown himself at a conference 2012 in Paris started a talk where he explained that formalism and said the motivic is very important for resolving all the issues of not being able to prove irrationality, let alone transcendentality of the multiple zeta values involved. But if you believe that they are all irrational and that can be proven and that you get a proper Q subalgebra, then you can slightly forget about the M here as long as you apply it. Now, this phi map is not unique, and I will write it down in a certain convention, and this convention is completely fixed by saying that any single zeta value should be translated into the letter Fn. And then we have a couple of different examples. So phi of zeta 3, 5 is precisely minus 5 F5 F3. We get another one, which I will write here because there's still some space left. There is something like phi of zeta 3, 7, which is minus 14 F7 F3 minus 6 F5 F5. And the last one, because I need the another feature, zeta M 3, 5, 5. So that's something at weight 13. Very few of you will probably have calculated objects which are at weight 13. Nevertheless, nice structures show up there. And this is minus 5 over 2 F5 times F3 shuffle F3 times plus a couple of other terms. So sometimes it pays off to actually write F3 shuffle F3, and you do exactly what you do with the letters 0 and 1 with the shuffle product of these F3s. So there is a beautiful article from Francis Brown in which this is explained. I'm happy to give you the reference afterwards. Now, one can show that indeed, once you have translated all your multiple zeta values into this F language, so a couple of terms I didn't write here, I just wanted the shuffle product here. Yeah? Thanks. I think this is 3, 3, 5 because I have 5 and 6 here. I think I mistyped here. Yeah, no, actually it's a 3 here as well. Thanks for pointing that out. Yeah, one better has the same weight on both sides of the expression. Now, when I had the Jenny, the secretary, sent you my 1,000-digit number for numerical experiments, I pointed you on a paper by Francis Brown and said, okay, we have this particular number here, and if you want to match it, then you should consult the basis of multiple zeta values in this paper by Francis Brown on page 4. I think I even wrote the page. And then try to match the expressions with the numerical expressions for the numbers. Who has succeeded in finding something? 2, 3? Okay. Yeah. What is the result? No, it's a couple of numbers, sure. But is it uniform transcendental weight, or so is it something which involves zeta functions of different weight, or is it? It's weight 8. Yes, it was a pure weight 8 thing I gave you, and then it is a nice prime number 1 over prime number combination. I'm happy to share that. In order to see that it is an easy combination, you better express zeta 2 to the power 4 in terms of zeta 8. That will make the numbers nicer. But I will give the solution at some point. Now, what you probably did then was you were taking the basis elements, typed it into Paris in order to get a long expression, numerical expression, somehow transferred that to Mathematica, or you used Paris right away, and got the solution from finding the null vector. Now, it is possible, instead of giving a basis in terms of the multiple zeta values in the language here, in terms of the f's. And that is what I would like to write down, basis for the space Z n. And let's make a table here. So we have n equal 1, 2, 3, 4, 5, 6, 7, 8. And then we can write down the basis elements. So for 1, we get a empty, so there is no basis, there's no element in the weight 1 space. And then it looks very similar first to the expressions you found in Francis Brown's paper. That is because we chose the phi map to map single zeta values to single letters, F2 and F3. For weight 4, we get an F2 squared. And for 5, it's F5, and then F3, F2. Now there is no choice choosing F2 and F3, because in the silent agreement, the words always collect all the even Fs at the end. Then at weight 6, one can have F3 shuffled F3. I'm sorry, I didn't ask, is everybody fine or familiar with the shuffle symbol? Does everybody know what that is? Please tell if not. Okay, good. And then there is F2 cubed. Then we get F7, F5 times F2, and F3, F2 squared for 7. And finally, there is F5, F3, F3 shuffle, F5, F3 shuffle, F3, F2, and F2 to the power 4. And of course, the dimensions of the respective spaces are equal to the numbers I have written down last time. Actually, Lance told me last time that in the generating series for the numbers, I had a minus arrow. So I think I wrote 1 over x cubed minus x squared minus 1, and it's the other way around. It's 1 over 1 minus x squared minus x cubed. Yeah, but you had a question.
Yeah, why do you bother writing F3 shuffle F3 instead of just F3?
I think this is just a fancy Francis Brown notation. I could easily write 2 F3, and the 2 for a basis wouldn't make a difference at all. It's, I think, in order to preserve the pattern F3 shuffle F5, which comes then at later weights, and you can actually see that the odd combinations of F letters usually show up with a shuffle in between. So if you have F3, F5, you usually get F5, F3 as well in the basis. And I think that's just a particularly nice choice. Yeah. Yeah. Okay, so let us just do an example for the G's, so or for the zetas. So I think the last time for the zeta values I had shuffled zeta 1 0, zeta 1 0 0. I Was that my example? I can't remember. I think so. And I had been writing that we have, or what one should think about. One has a ordered list 1, 0, and an ordered list 1, 0, 0, and then you start to shuffle them by taking the first element of the right list and leave it at the position it is. So the first element you would get is just the concatenation.
In the context of the F, that I don't have this list of numbers.
I'm sorry. Then I got you wrong. So this is clear how it works. Okay. I'm sorry. Yeah. So if you have F3 and F3, shuffle F3. F3, shuffle F3. That would have two one-element lists, F3 and F3. So you would get the concatenation of those two as the first element. That's one way of doing it. And then you could take this element and move it past the left element, and you would get another F3, F3. And Lance's question was exactly, why do you bother to write F3, shuffle F3, when you could just have one element? And my answer was, if those are not equal, then you get F5, for example, F5, shuffle F3, and it is a fact, if you look at the table, that the shuffled things always show up in the combination where you have the two shuffles simultaneously as a basis.
I forgot that they were not commuting on this axis.
Yeah, it's a good point. One has to get used to this kind of way. So I wrote it's a linear combination of words with letters, and these letters do not commute with each other. So the succession matters. For the even Fs, that's a different issue, because all the even Fs, they commute, and you can, yeah. Okay, further questions?
But isn't that since they are anti-commutative? I mean, can you have more than two Fs?
Yes.
Shuffled, right?
Yes. You can, for something have F5 shuffle F3 F9. Yeah. Then now, if you were picky, you can say, oh, it's still an anti-commutator, and of course it's true. You can represent each shuffle relation as a linear combination with dedicated signs of anti-commutators or commutators, depending on what you want. Yes, these things do exist, and it is a useful notation. Mm-hmm.
Is this something I can deduce from this shuffle definition?
No, you can't deduce that from the shuffle definition. So what you do is you apply the coaction, which is related to the underlying algebraic structure, to the multiple zeta value, and then there is a purely analytic way, actually, of writing down what that coaction is. There's also a nice geometrical / graphical way of finding out which terms actually contribute to this coaction. This is something which is another implementation of the symbol algorithm, if you want so. So in the same way as you dissect or take apart a polylogarithm using the symbol by using the coaction on the polylogarithm, you can take the coaction on the zeta value and somehow pull out the ingredients in a particular way, and that will lead to all the funny coefficients. So you would be a wizard if you were able to guess these things. So it is not really straightforward. For very easy examples, it might be possible. I can't do it. Now, we have this F alphabet now, and this is, I would say, the most sophisticated and mathematically clean and beautiful way of writing down the basis for the fixed weight ingredients to the graded Q space of multiple zeta values. And a general question one could ask in that respect is, what actually is a basis with respect to the shuffle relations? So you are handing me a set of properly regularized integrals, which are iterated integrals with respect to a set of differential forms. Let's call this set of differential forms letters. And you ask me, or somebody else, what is a basis with respect to these shuffle relations? And that is a concept I'd like to spend 10 minutes on, because that is, again, something where one can have a lot of fun trying out. And it is a rather advanced and beautiful mathematical concept which has a very, very simple explanation. So this is called a basis with respect to shuffle relations. And this goes by the name of the London basis. And this London basis has been invented or found by Roger London in 1954. And the starting point is the following. Define an alphabet and this alphabet is an ordered list. That is, you get a couple of letters and you define a succession of these letters. So for our example, that will be 0 and 1. But at the same time, one could also think about A, B, and C. So the ordering in this list doesn't need to have anything to do with the ordering which is natural. So you can also take mu, b, and aleph if you want, whatever. It's just the position in the list which makes the difference here. And now let us define what a London word is. So a word made out of these letters is a London word if and only if for each decomposition W equals UV with U and V non-empty. So that's the empty letter, the empty word. If for each of these decompositions you can show that U times V is smaller than V times U. And this smaller refers to the ordering in this alphabet, and for almost all situations this will just be the lexicographic ordering. So if you have a word, say we take a word from the 0-1 alphabet, you can, let's take the word 0-1-0-1-1, which I claim is a London word. So we can take the word and divide it at various places. So what looks like a product here is concatenation on the letters. So I divide here, and indeed this is smaller than 1, 0, 1, 1, and then the 0 put to the very end. The same is true for 1, 1, and then you get 0, 1, 1, bar 0, 1, and again this will be smaller. And you can go through all the other examples. Actually, we are almost done. 0, 1, 0, and the last one 0, 1, 0, 1 divided here is smaller than 1, 0, 1, 0, 1. So that is obviously a Lindenwert. Not clear?
I'm just a little confused as to what smaller means.
What smaller means? It means lexicographically smaller. And if we interpret this 0 and 1 as, say, binary numbers, we have one lexicographic ordering here, and that satisfies the condition for all of those. So if you look at the binary thing, this is 8 plus 2 plus 1. That's 11. And this is smaller than 16 plus 4 plus 2. So you consider the whole word. I just made these bars in between in order to mark where I divide the word in UV and in VU. And all the relations, if you convert the binary numbers to natural numbers or base 10 numbers, will be true. But that can also be done for an alphabet, and you simply take the lexicographic ordering if you have letters A, B, C. So the ordering is defined here with the succession of the letters in the alphabet, and then you take the lexicographic. How many of these words are there? We'll answer it in a minute. There's a second statement saying that every word W can be represented as a linear combination of Lindenwerts of equal length and shuffles of shorter shuffles of Lindenwerts of shorter length. Or I should write smaller length. One can give it a try, but of course a mathematician would like to know how to actually first of all calculate these Lindenwerts and find a representation of these Lindenwerts. And since this is one of the really easy algorithms, I will spend another 5 minutes in telling how that actually works. And that is again one of those things which I would ask a little problem or where I will have Jenny send a little email. Now, after the next 5 minutes, you'll be able to create Lindenwerts with respect to an arbitrary alphabet. And that is, you can basically create the Linden basis up to a certain length. And I will write down an expression in terms of the alphabet ABCD. So we have a 4-letter alphabet, and would like to ask you to express that in a Linden basis with respect to the alphabet ABCD. So I'm saying that at the very beginning because it might be advantageous to have that in the back of the mind for the next minutes. So the algorithm which delivers Lindenwerts up to a certain length is called the Duval algorithm. And while one would believe that this is a very old insight. We are getting now a little closer to the time we live in. This algorithm was initially published in 1976. So it's something which is related to the shuffle product, and maybe the shuffle product wasn't as popular before. The algorithm is as follows. Start with a word W, and before doing so, fix the alphabet. That should be 0 and 1 in our case. And you also want to fix the target length. That is the largest length of a London word you want to produce. So let's say this is, in our case, 3, and I want to call this n. So you start with the word W and repeat the word to produce a word of length n. Then remove the last character or letter. If it is the last letter of the alphabet, and repeat it until the last letter is not the last letter of the alphabet anymore. And then last step is replace the final letter with its successor in the alphabet. Okay, let's do an example and start with a very easy word, and the easy word is just the word 0 here. Now in the first step, I start from the word 0. My target length is 3. So I want to write the word a couple of times after each other until I reach 3. If I would have a word of length 2, I would just write the word of length 2 and then the first letter of the word again. Then I would have gotten the right target length. Now, remove the last letter if it's the last letter of the alphabet. The 0 is, of course, not the last letter of the alphabet, so I'm not supposed to remove anything, but can go to the next step, which tells me to replace the final letter with its successor in the alphabet. So that will lead to 0, 0, and 1. And 0, 0, and 1 is the next London word, and I will square that. Now, I can repeat the algorithm. I take 0, 0, 1. I write it a couple of times after, in a row, but I already have the right target length. Then I scratch out the last letter because it's the last letter of the alphabet. I end up with 0, 0. And then I replace the last letter by its successor. So I get 0, 1. That's the next London word. And let's do one more. Taking 0, 1 will result in 0, 1, 0 of length 3. The last letter is not the last letter of the alphabet, so I don't scratch that out. But I replace it by its successor, and I get 0, 1, 1. and that is the next Lundenwert. And eventually, and one can prove that this is the case, this will cycle, and you will get, again, you will exhaust the space of Lundenwerts. Now, what is a typical basis for the 0 and 1 alpha bit? I'll just write down up to length 4. That is 0, 1, 0, 1, 0, 0, 1, and 3 zeros. And then there is also 0, 0, 1, 1, and 0, 1, 1, 1. And that's all. And if you want a Lundenwert which is not only first a couple of zeros and a couple of ones, you have to go to length 5. An example is up there. And the same thing you can do for an alphabet ABC or an alphabet ABCD. And so this will be something which I would like to encourage you to try out. So code up this Duval algorithm. That's simply a loop with a couple of list manipulations in Mathematica. You don't need to do it for a general alphabet, just choose one, and then put all these Lundenwerts out there, and then try which combination of shuffles of those words actually leads to the word I will send around with an email tomorrow. Yes?
So you said now that every word can be represented as a linear combination of these, but you haven't actually told us how to add words.
How to add words. When I say a linear combination, I should have said a Q linear combination, or in that case, I could actually have an, can I have it? No, it's safe to say a Q linear combination. Yeah, so you multiply, you take 3 times the object.
But what does it mean? I mean, how would I decompose 1, 1, 1 in this list basis?
How would I decompose 1, 1, 1 in the Lunden basis? You would say 1 is a Lundenwert, and then you would use 1 shuffle 1 shuffle 1, or 1 to the power 3, and you would be done. Yeah. You had a question as well?
I think you just forgot to transcribe the 0, 1, 1 into your...
Oh, yes. Thank you. Thanks. Yeah. Yeah, good. So this is a problem which will probably take some time. Yeah? It's not really trivial, but if it comes to programming, it is something which is total standard. And I would expect you can do that within an hour or something like that. If there's trouble ahead, just drop me a line or ask me tomorrow. I'll be around, and I'm happy to help if there's something difficult on. Now, we have almost everything which we need at genus 0. We have the multiple zeta values. We have a beautiful way of writing it in a basis mathematically. There's an algorithm which tells you how to identify a basis given a certain alphabet, and that's applicable not only for the zeta values, but also for polylogarithms and appropriate letters for this. But there is one thing which you might have heard of, which we need in order to round up the genus 0 discussion, and that is the so-called single-valued multiple zeta values.
By the way, Johannes, the limited basis there also applies to the MTDs. If you just delete everything that's 0, or if you cover this table of axes, what's the same dimension?
It better should, actually. So yes, you take the Fs as your alphabet, and then you need to apply the weight grading in order, of course, to single out which Fs are candidates or which combinations of Fs are candidates. And then I'm sure you can just choose a Lunden basis. Can you say it again louder?
Where it says it's not, they also have the border shown as it is. And so here you have 0, 0, 1,
Yeah.
1, 1, right? Zeta 1, 2, zeta 2.
Yes, so the answer to what you tried is no, because exactly for the reason Eric mentioned. So if you would translate that into MZVs right away and then try to map it, you are missing one part of identities between MZVs. But if you would start with the letters F and take into account what I erased, that the F2s are in the co-module, then everything will result in something which should be this table. Okay, single-valued zeta values. Now, this whole expression is a little a strange expression because zeta values are values. We have shown, or I've mentioned, that they are real numbers. And how can a number be single-valued? A number is usually always single-valued. And of course, that is an expression which goes back to the fact that the zeta values can be represented as special values of polylogarithms. And these polylogarithms, they, in general, are functions with a rather intricate branch cut structure. In particular, if you integrate over many of these differentials, you get branch cuts all over the place in weird linear combinations. So your whole plane you're considering is crossed by various branch cuts here and there. And sometimes it's very difficult to write down where you are, on which sheet you are. But there are amplitudes, and this happens for particular kinematical situations. That happens also if you look at gravitational amplitudes, which seem to be expressible, and that is true for many examples, in a subclass of the multiple zeta values, which are exactly these single-valued multiple zeta values. So the statement is there are classes of amplitudes which can be expressed in terms of a subset of the full multiple zeta values. And these, the idea behind the single-valued zeta values is the following. Let's define a single-valued polylogarithm. So this is noted by the SV at the letter G. It has a label, and here I would write 0, and this is an object which does not only depend on Z, but also on Z bar. So we are leaving the realm of holomorphic functions. We are thinking about a complex plane here, and this one will be defined as G0 of Z plus G0 of Z bar. But now one can rewrite this and simply write it as logarithm of Z plus logarithm of Z bar. That is a result whose validity can be shown thinking again about regularization. And this is, of course, the log of Z bar, and that is a function which doesn't have a branch cut. It just has the divergence at 0. How does that come across? Sure enough, if you draw a picture for the, so that's an x-axis or real part axis and a y-axis. If you draw a picture for the Riemann sheet you're considering, I would like to put my branch cut on the negative axis, and then I choose the Riemann sheet to be like that. So when I walk in the positive direction, I would like to have this as the Riemann sheet for the logarithm and get the branch cut or the jump here. Then at the same time, I could do that for the log of Z bar. And for Z bar, it will actually be the other way around. And if I combine these two Riemann sheets, of course, the branch cuts will cancel, the jumps will cancel out, and I get a single-valued function. Now, this is a neat concept, and as long as you only have one integration, it is very easy to find out what these functions are, what the single-valued polylogarithms are. It gets a little more difficult once you get to greater weight of the zeta values or more integrations in the integrals. So for example, you can show that G single-valued of 0, 1, 1 at of Z and Z bar is just G of 0, 1, 1 Z plus G of 1, 1, 0 Z bar plus G of 0, 1 Z times G of 1, comma Z bar plus G of 0, comma Z G of 1, 1 for Z bar. That's nice. So look at the label here. It's 0, 1, 1 with Z, and it's the reversed label with Z bar. And then somehow the rule seems to be that you have to cut the label at any inner position and combine it in a product of G of Z and G of Z bar. So 0, 1, 1, 0, 1, 1, the labels are still there. And you might even say, beautiful, I can, and we had this discussion during the coffee break, I can guess a rule here. And you would be very disappointed if I write down the next expression, looking at the single-valued polylog for the label 0, 1, 0, 1, you would get exactly what you would expect. It's 0, 1, 0, 1 for Z plus G of 1, 0, 1, 0 for Z bar. And then you get all the combinations. So it's G of 0, 1, 0 for Z, G 1 for Z bar. And then there is G0 of Z and G101 of Z bar. And then the product were divided in the middle, which is G01 of Z, G of 1, 0 for Z bar. And so far, the rule which you could guess is there immediately. But then comes, unfortunately, a very little disturbing term here. So that's G1 of Z bar. And one does actually understand where that term comes from. There is an equation and a mathematical way of determining how these combinations or these linear combinations of polylogarithms have to be in order for all the branch cuts to cancel. So it is a certain so-called monodromy condition which allows you to infer how these polylogarithms are built up. Now, back to the single-valued zeta values. I've talked about single-valued polylogs. Not surprisingly, the single-valued zeta values are precisely the single-valued polylogs evaluated at Z equals Z bar equals 1. So should we have a short break, or is it already too late for a short break? What do you want? This would be a good spot. Shall we have just a 2-minute whatever, wipe the blackboard break and then? Okay, good.